Let's explore availability and reliability. We'll cover the critical distinction between availability and reliability, error budgets and the math of nines, failure modes that break these properties, and designing for high availability using redundancy and failover. Let's get started. When people say a service is good, they often mix up two different things. Availability is, can your server respond right now? Reliability is the response actually correct? Availability is just uptime divided by total time, and that's what nines are measuring. 99.9% sounds great, but it still allows about 43.2 minutes of downtime every month. Reliability is about failures over time. So we talk in MTBF and MTTR, mean time between failures and mean time to repair. Availability is roughly MTBF divided by MTBF plus MTTR. That's how two systems can both hit 99.9% but feel totally different. Here's the trap. Your service can be up and answering every request, but still be unreliable for users. A cache can happily return an outdated price after the database changed, and your dashboards still show clean HTTP 200s. In production, Cloud Object Storage shows the split perfectly. Your data can be replicated across failure domains for extreme durability, while the API you call still only promises, say, 99.99% availability. Getting both more correct and more up usually means more replicas, stricter coordination, and a lot more cost. So when you promise an SLO like 99.9% availability, you're also admitting something. Some requests will fail. That allowed failure is your error budget, and it's what lets teams move fast without ignoring reliability. Here's why adding a 9 gets brutal. In a 30-day month, 99.9% gives you 43.2 minutes of downtime, but 99.99% gives you 4.32 minutes, and 99.999% is basically 26 seconds total. Now the painful part. End-to-end availability multiplies across dependencies. If A, B, and C are each 99.9%, your user sees 0.999 times 0.999 times 0.999, which is about 99.7%. You just lost a 9. SRE teams track error budget consumption from real metrics like success rate and latency all month long. If you've burned 80% of the budget by day 20, you stop shipping risky changes, freeze deployments, and buy reliability back. And that's why extra nines aren't linear. To move from 99.9% to 99.99%, you often need multi-region active deployments, independent failure domains, automated failover, and 24/7 ops. That usually means 2x to 3x cost. Most outages are obvious, like a server crashing. Gray failures are nastier. An instance looks healthy to your load balancer, but real user requests misbehave, so reliability tanks while dashboards still say everything is up. Here's what makes it gray. Instance B still returns HTTP 200 on its health check, so the load balancer keeps routing traffic to it. But 30% of real requests hang for 10 seconds or return subtly wrong JSON, so users see timeouts and bugs. So instead of just asking, is the process alive, you watch multiple signals per instance, track success rate, and track P99 latency, meaning the slowest 1% of requests. Also watch saturation signals like queue depth and run a synthetic canary that constantly hits the real endpoint. Now you can automate the reaction. If one instance's tail latency blows up, you evict it from the load balancer target set, even if its average latency still looks fine. That one rule prevents a single, half-broken machine from poisoning the whole fleet. The punchline is simple. Uptime isn't the same as reliability. A basic liveness check only catches crashes, but gray failures show up in success rate, P99 latency, and saturation metrics, plus canaries that hit the real request path. High availability starts with independent failure domains. That means deploying across multiple availability zones where each one has its own power, cooling, and network infrastructure, so a single event can't take everything down at once. When one zone fails, the remaining zones need to absorb that traffic without overloading. That's why you maintain 30 to 50% surge headroom, so if you lose one zone, the others can handle the extra load and stay operational. Active-active means all replicas serve traffic simultaneously, giving you zero failover time, but it costs 2 to 3 times more capacity. While active-passive keeps a standby idle, which is cheaper but takes 30 seconds to several minutes to failover, and you get cold cache performance. Here's the thing. Your mean time to repair dominates availability way more than how often things break. If your system fails every 6 months but takes 4 hours to fix, you get 99.91% uptime. But reduce that repair time to just 10 minutes and you jump to 99.998%. Synchronous replication waits for replica confirmation, which guarantees zero data loss but doubles your write latency, adding 1 to 5 milliseconds, while asynchronous replication keeps writes fast by replicating in the background, but you risk losing seconds to minutes of data if the primary fails. So to recap, deploy across independent availability zones with surge capacity to absorb failures. Choose active-active for zero failover or active-passive for lower cost. Automate detection and failover to keep recovery under 10 seconds, and pick synchronous replication when you need zero data loss or asynchronous when speed matters more. Thanks for watching. If you enjoyed learning about availability and reliability, hit subscribe for more system design fundamentals. Catch you in the next one.